Hi, this is Jim Johnson with Siliconade, and I thought I'd put this quick little video together on how to deal with multiple taps within a chip. This is because each year we get a lot of questions on how to make this work, and we also see several companies who've basically screwed this up, and we need to help them try to fix it. So there's lots of different ways to handle multiple taps. I'm going to explain one way that's the most straightforward, the most easy to implement. Okay. So here's our multi-tap problem. We have a SOC. It has our standard 5 JTAG pins as described with 1149.1. It has a compliant 1149.1 tap controller, boundary scan register, everything that you would need to be compliant to the 1149.1 spec. We also have inside this SOC a microprocessor, whether it be an ARM or any other processor that you can buy in the market or an internal one from your company, and some type of a high-speed SerDes, and it also has its own JTAG tap controller for both of these pieces of IP. The question is, how do I successfully and easily connect these and have them run from the tap pins? Okay. That's what this quick discussion's all about. So what's my basic assumptions in this presentation? So let's keep it simple. We're going to make something that works, is very generic. You can apply it to one or more internal JTAG controllers. Okay, you can have 100 if you want with this method. Okay, you can use and share the chip JTAG pins for all the internal JTAG controllers. Okay, the ability to run each JTAG controller independently. So we're going to run tap controller 1, tap controller 2, and they're not going to interact. Okay, in case we want them to, and we'll talk about that a little bit later. So we want to use a known, proven, general approach to access all of these tap controllers. Okay, hopefully in a way that's simple to understand and simple to implement, and even more importantly, simple to verify that it all works. Okay. The other assumption I'm going to make for this discussion is all the pads for the boundary scan ring are not within hard pieces of IP. So the chip integrator who makes the boundary scan ring can get to all the pads and they can connect them up correctly. Okay. If you have a boundary scan register within a piece of IP that's a hardened piece of IP, we need to have a separate discussion on how to handle that. Okay. Not covered in this presentation. So what's my basic questions that I need to answer? What logic do I need to multiplex all the JTAG signals in and out to get it to the 5 chip pins, right? How do I, after I get the logic in to be able to select it, what do I have to drive on the pins to be able to select each one of those tap controllers and make them active? Okay. And how easy is it to check and verify that all the taps work by simulation and by creating test program patterns, production test level patterns, to make sure everything works? So let's start off with, what logic do I need? Okay. So first and foremost is a bit of advice. Don't simply daisy chain all your JTAG controllers together and assume it's going to work. You should assume it is not going to work. Okay? It's not going to work. It's not going to be JTAG compliant. That doesn't mean you can't do it. That means there's a lot more work that you need to do that's not in this presentation. Okay? So we basically have two options for how to control the selection of which tap controller you're talking to. Okay. One is to use compliance pin. It's the most straightforward way to use compliance pins to be able to select which JTAG controller you're going to talk to. Okay. So to do this, you must have extra pins, extra package pins available to be able to do it. So if you have extra package pins and you can add them just for this feature, that's great. There would be no need to do additional JTAG instructions to support this. And the downside is typically you can't really control compliance enable pins at the board level or the system level. You know, there might be exceptions to that. You might be able to program it depending upon what vendors you're using and what your apps board looks like and what you're doing, you know, what system it's in. But in general, you can't toggle these pins at the board or system level. So if you're only doing testing of multiple taps for ATE test and in-house testing of the actual chip by itself, you can get away with just doing compliance pins. And it's a little more straightforward. Okay. Option 2 is you can have a private instruction or instructions to control the selection of which tap controller you're going to talk to. And that's what most of this quick discussion is all about. Okay. So I say this in a couple of places. The default controller, the default JTAG controller, needs to be your chip level JTAG controller. And that's the JTAG controller that's defined with your BSDL file description. Okay. So at startup, at power up, T reset, it all needs to go back to your chip level JTAG controller without doing anything. Okay. You can't toggle more pins and then it goes to that. It's got to come up from power up and directly go to that JTAG controller. If you don't, you are not IEEE 1149.1 compliant. Okay. So just keep that in mind. So what's the general approach that I'm suggesting? And again, there's going to be lots of different ways to handle multiple taps. Okay. This is our simplest way. We're going to borrow Chapter 15 from the IEEE standard 1149.7. Okay. 1149.7, not a lot of companies use. There's some good reasons for not using it. Basically because it's just so huge. It's 1,200 pages of the standard. It's hard to implement. So a lot of people don't do it. But the .7 standard does have a few really good key ideas in it. One of them is how to simply control multiple taps. So we're going to steal that out of the standard and use that technique. It's not required to be 1149.1 compliant. It's still compatible with 1149.1. You're not going to violate anything in 1149.1 if you do this method. Okay. For verification, I'm going to talk about this at the end, and pattern generation. The reason we get asked this question a lot is because our tool suite has a special mode built in to support automatically selecting which tap you're talking to. Okay, and I'll talk about that a little bit later. It is not required, using our tools is not required to use this technique and this hardware that I'm going to explain to you. It just makes it easier. Okay. So this technique will work with any compliant JTAG controllers from any source. Okay. If you get your SerDes JTAG controller and your microprocessor JTAG controller and your chip level controller all from 3 different sources, as long as they're all compliant, this should work. Okay. This technique that I'm going to describe, and it's again very simple, can work with using compliance pins. It can work with using private instructions to select and control access to your JTAG controllers and your taps. Okay. So either one works fine, and I'll show you the two little diagrams on how they both work. And again, there are many, many ways to make multiple taps work. This is just one. I like it because it's very simple. It's very straightforward. Everybody understands it. It's easy to program. It's easy to verify. Okay. So we already talked about the pins we're going to use. We're going to use the 5 standard JTAG signals. If you don't have a T reset, you can still use this technique with 4 pins and just do 5 TMSs to do a reset. Okay. We're assuming, this is an assumption, that the TDO pad that's at the chip level, you have access to the inputs to that pad. So you have the access to TDO out and you have access to TDO enable. And to do this, it's required. To basically do anything with multiple taps, this is going to be a requirement, okay? Because you've got to be able to multiplex out those outputs through TDO somehow, okay? So here's an example of a implementation, and this is for compliance pins. So notice I've got 3 compliance bits here, and I'm showing you how to use them within your SOC, okay? And again, the problem with compliance pins, or a challenge with compliance pins, is you must have extra pins available, okay? And you typically cannot control compliance pins at the board and system level. So again, if you're going to use it at the board and system level, this is probably not the best approach. A private instruction is better, okay? But let's go ahead with compliance pins. So you've got a number of compliance pins, and this is expandable, okay? I've shown, in my example that I had earlier, I had 1 chip level JTAG controller and 2 other blocks that had JTAG controllers. I had a multi-processor and I had a SerDes. You can expand that to as many as you want with this technique. You just need more enable bits. You can also take your enable bits and decode them. For example, if you had 3 enable bits, that will allow you to drive 6, and you have to reserve the 7th for the chip tap to be all zeros. Okay. So I've shown the decode logic on the side here. If you have compliance pins and you have 3 pins and they're all zeros, this is going to reset back to the chip level JTAG controller. And all zeros on those 3 pins must be in your BSDL file. Okay. If it's not, it won't default back to your chip level JTAG controller, and you will not be IEEE compliant. Okay, so that's important, and I keep repeating it. I've also shown the decode for block 1, block 2, all the way to block N. Okay. Notice there is a couple of blocks that are in this block diagram. First, think about this as your microprocessor JTAG controller, your SerDes JTAG controller, and your chip JTAG controller. Hopefully you can see my mouse moving. And you have some logic that will mux in the correct TCK clock to whichever block you're talking to, okay, based on your enable pins. And you have some logic that will help you mux out your TDO and TDO enable back to a central small little JTAG IO block so you can correctly get out which TDO is associated with the JTAG block you want to talk to, okay? It's that simple. And this is, again, using compliance pins. Okay. Let's say that you don't have extra pins, or you need to use this technique in board test. Okay. So you have almost the exact same circuit. Notice this time I've got a private instruction register, and it also has an amount of bits. I've got my microprocessor JTAG controller, I've got my SerDes JTAG controller, I've got my chip level JTAG controller. The logic in the TCK clock muxing and the TDO muxing is exactly the same. Okay, so the whole circuit is exactly the same, other than where do I get these enable bits from? Do I get it from a compliance pin, or do I get it from private instruction? Okay, same rule applies, that whatever this register is, when it is reset on power up, it has to power up to, and in my case, all zeros, which goes back and selects the chip level tap. Okay, you can make this whatever you want to. You just have to make sure that the resets for these bits reset back to give you the chip level JTAG controller. Okay. Yeah, I think that's all on this slide. So again, the exact same circuit, very small, very easy to understand. And it's straight out of the 1149.7 standard. So it's well documented. Okay. So let's talk a little bit more about the block diagram for this implementation. So we're going to have three signals that are the three of the 5 standard JTAG signals that are going to go to all the blocks. Okay, T-reset, TMS, and TDI all go in parallel to all my chip level JTAG controller, my microprocessor block, and my SerDes block. Okay. Each one of these blocks has a separate TCK that gets generated. It has a separate TDO that comes out, and it has a separate TDO enable bit that comes out. Okay. And it goes into this very small little JTAG IO block, which you can put anywhere. And I'll show you the logic that is within this block, but you'll see that the TDO bits, one of them will be selected, and one of the TDO enable bits will be selected, right? You can't just tie these together. Okay? You'll have contention all over the place. All right? So what does that little JTAG IO block look like? You can think of these as muxes if you want to, where it's got 2 enable bits per mux. I've drawn the little logic expression out to the right here, and I implemented it with little AND gates. You can do it however you want to. It's very simple little RTL code. You can do it with nested if statements. You can do it with case statement. You can do it with logical expressions. You can instantiate a mux, however you like to do it. It's very simple. Okay. Some issues that I have down at the bottom here. The isolation register is a JTAG register with capture and update. Okay, we've sort of talked about that. It's a private instruction, and it must be reset back to the chip level JTAG controller on power up or T reset. Okay. The above logic that I have, notice I'm decoding all bits. So you can only turn on one of these taps at a time with this implementation. Okay. If you didn't do this and you just said the enable bit is bit 1 for the first JTAG controller and it's bit 2 for the second JTAG controller, that would work, but you have the possibility of turning them both on at the same time. So one, we don't know what's going to happen if you turn both of them on at the same time in a general approach like this. If you intend to use more than one JTAG controller at a time, more than one tap, be very careful. This is where most people mess up. Okay, you must add additional logic to orient the enable bits. You're going to have to mux out TDOs so they're daisy chained. Verification gets a lot more challenging when you do this. Okay, it's much harder to implement, much more harder to automate. If you're going to do this, shoot me an email and we can help you. Okay. Not covered in this discussion. So let's go back to my original example where I've got 5 JTAG signals. I've got a chip-level JTAG controller. I've got a SerDes with its own JTAG controller, and a microprocessor with its JTAG controller. If I add my JTAG I/O block that we just previously discussed, it's going to go somewhere inside your design. It doesn't have very many gates in it, less than 100. But it's between your chip-level tap and your other JTAG tap controllers. Okay, and that's it. Very, very simple implementation. So one of the hardest things to do with multiple taps is to verify that they actually work when you put them inside your SOC. So most of the time that you're going to spend is trying to make sure that you didn't screw it up. Again, the chip taps got to be available on PowerUp by the standard, period. So you've got to make sure that happens. We intend to isolate and verify each JTAG tap controller individually. I think this is a good idea for everybody to do, even if you want to have another mode that daisy chains something else together. Okay? You want to make sure that you can test them, generate patterns for each individual one, at least with one test mode. Okay? Automatically control which tap is active and generate a self-checking test bench and matching production patterns automatically. So I've seen companies have a really clever, really complex way to handle multiple taps, but they spend weeks and months trying to verify that it actually works. So an automated fashion is going to be highly recommended by SiliconAid. So to be able to leverage doing scripting and other automated repeatable means of verifying all your taps work via simulation is important. Doing regression tests, so when you have another spin of your chip level netlist, you can automatically run a regression test to make sure all your taps still work and those connections weren't messed up in some way. So here's my disclaimer again, because I don't want anybody to yell at me. There are many ways to accomplish making multiple taps work. This is just one. It's a very simple one. Okay. So the verification solution is where most people spend most of their time if they haven't thought this out before they start. Okay. So what we want to do with this simple implementation is create a simple preamble, and I'll tell you what I mean by preamble, for each one of the quote-unquote internal slave taps. And in our example, that would be the tap for the microprocessor and the SerDes. Okay. To initialize all the compliance pins, if you chose to use compliance pins, or if you chose to use an isolation register with a private instruction, or a combination of them, to select the tap correctly each time. So a preamble for us is just a very small file that describes how do you select which tap you want to talk to. And this little file, you're going to have one per tap inside your design. Okay? You don't need one to talk to the chip level tap because it's going to come up by default on PowerUp or a T reset. Okay? But for all your other taps, and I'm going to call them slave taps, you're going to need one of these little preamble files to say, drive these pins in this way, and then you're only going to talk to this tap. Okay? So our tool, which is called JTV, will automatically apply those preambles every time during the tool execution of a mode. And a mode for us is you want to talk to tap 1, you want to talk to tap 2. So you're going to pick the tap, and it's going to execute the preamble every time on PowerUp. When you execute a T reset, like one of your JTAG patterns has a T reset in it, or any other time that you change something that could affect the tap selection, the tool will automatically return control to that JTAG controller you told it to do it, okay, automatically for you. It'll put the patterns in, it'll put the simulation in to make sure that it works, okay. It'll automatically generate a full suite of simulation and production tests for each tap, okay. Very simple, very straightforward, very fast, okay. So that's it. Very simply, it's an easy implementation of multiple taps, okay? Things that we did not cover today, and I mentioned them sort of as we went, access to more than one tap at a time. So if you want one tap in test and one tap in X test, and they happen to talk to each other, that was not discussed. Give us a call or shoot me an email. I'm going to leave my email at the end, and we'll help you if you need help. Okay? Switching between taps without a T reset. So in the implementation I showed you, if you just did a T reset, it's always going to go back to your chip level tap, and then you'll have to reprogram the compliance pins if you use compliance pins, or you'll have to reprogram your private instruction and shift your enable bits back in to select the other tap. Okay. If you want to do that more seamlessly and talk to multiple taps, or switch from the chip level tap, go to a secondary one of the other taps, one of the slave taps, and then go back to the chip level tap and keep doing things, that's all possible. Okay. We just haven't discussed that. Parking taps, sort of along the same lines, where before you leave a tap, you're going to put it in something like run test idle. So it's going to just sit there and spin until you come back and reconnect to it. Okay. Security concerns, which is a big issue that we haven't talked about, is it's great to talk to all of these taps, and now you have access to all their tests through a standard that everybody knows about. So there's a lot of security concerns when you talk about any standard that gives you access to internal IP. And we can help you with that too. Remember at the beginning I said the boundary scan register bits are not in hard IP. What happens if they are? Then you have to do some other things to make sure that you can test that section of the boundary scan register bits, and we did not cover that today in this quick discussion. So for all of these topics, I think Silicon Inc. can help you if you need those, if you need another opinion. Okay. And I put my email down here. Please email me. If you call me, I may or may not answer it, but if you email me, I will always answer it. And I hope this helps you a little bit with how to implement multiple taps in a very easy way. Good luck. Good JTAGing.